Hey there, welcome back to Calculus. In this second day of section 5.4, we're going to talk about something called the Net Change Theorem. It's really not a new idea. This is kind of a chance, again, to kind of catch up and digest some of the ideas that we've been talking about. So you can see the learning objectives I've got there. I want to understand the statement of the Net Change Theorem. It's really just kind of a specific instance of the fundamental theorem of calculus. I want to be able to interpret the meaning of definite integrals in context. We'll look at several contexts, including hydrology, chemistry, biology, physics, and there are many others. We'll look at those just few. And then I also want to be able to analyze the units on a definite integral of a rate of change. So we're going to talk about units throughout all of our examples. And then you can see I've added a fourth one. This is just a specific context from physics, but I want to be able to calculate, given a velocity curve, the so-called displacement of a particle and the distance traveled by a particle moving along the line. Okay? So let's get started with the statement of the theorem. Here's what the net change theorem says. It's just the fundamental theorem of calculus applied to a very specific kind of integral, the integral of a rate of change. So let's take a look at it. It's you're reading the statement. It says the integral of a rate of change is the net change. Okay, well, yeah, let's just kind of decode that here. Where is the rate of change? The rate of change we know in our calculus class is a derivative. So the integral of the rate of change the author is denoting by this capital F prime of x. It's a derivative. And then he's saying that that's the net change. Well, the net change in F, really. It's the net change in F, the thing that we're taking the rate of change of. And what's the net change in F? Well, it's just the value of F at the end of the interval minus the value at the beginning, right? That's how you would calculate net change. Like, for example, if F is the balance of your bank account, you could kind of think of this is the balance of my bank account at the end of the month minus the balance of my bank account at the beginning of the month. Well, that's the total change in my bank account. That's what they mean by the net change. That net change might be positive. It's positive if the value at the end is bigger than the value at the beginning. It might be negative. If it's the other way around, the net change might be zero. If capital F of B and capital F of A are the same, the net change might be zero, okay? Here below it, I've just written this in sort of more Leibniz-like notation. It's just, again, saying that the integral of a rate of change, I've called my rate of change df dx, and you integrate that with respect to x, well, it's the net change in F. It's the end minus the beginning value. Okay, so for this reason, the fundamental theorem of calculus is sometimes just called the net change theorem. It's called the net change theorem when the thing that you're integrating is itself a rate of change, when that thing is a derivative. Let's look at some examples in context. I liked this one from your book. It's an example from hydrology. Okay, so we'll just kind of walk through together. V is the volume of water in some reservoir, it says. Okay, so V of T is the volume of water. I made up some units for this. Let's say the units on V would be, say, cubic feet. It's not uncommon in hydrology for people to measure quantities of water in cubic feet. So maybe that's the units on this thing. In a reservoir at time T. So I put some time units on it. I said minutes. So the units on T might be in minutes if we inserted those. So this is just kind of a review question. What are the derivative on rates of change, right? Here, the output function is V. It's the output of the function. The input is the variable T. And the units on a rate of change are always units of output per unit of input. So the units on V are just cubic feet per minute. Yeah, if you're a whitewater rafter or something like that, you look at Trinity River flows, you're used to these units, or sometimes even cubic feet per second, right? CFS, this is a typical, but I'm going with cubic feet per minute here, filling this reservoir. So what does this integral, how do we interpret this integral here? The integral of V prime of T is V of T2 minus V of T1, where we integrate from T1 to T2. Well, the author is telling us the integral of that rate of change is just the net change in the amount of water in the reservoir. So V of T2 is how much water is in the reservoir in cubic feet at time T2. V of T1 is how much was in there in cubic feet at time T1. So their difference is the change. So this is how much water entered the reservoir or left the reservoir. It could be a positive or a negative number between those two time intervals. So it's the change in the amount of water. So in this case, that net change is the change in the amount of water, the change in V. All right. And you can look at an integral and kind of see what its units are computing. I'm going to make this slide a little messy here, but if I just write the units here, the units on V prime of t, we wrote down below, it's cubic feet per minute. And the units on t itself are minutes. Well, when you multiply cubic feet per minute by minutes, the quantity that you get is cubic feet. So this output answer, the change in V, should be in cubic feet. So you can always, quote unquote, dimensionally analyze an integral like that. You can ask yourself, what are the units on the function that we're integrating? Cubic feet per minute. What are the units on the input variable? Minutes. Well, cubic feet per minute times minute is cubic feet. So it sort of makes sense dimensionally. All right, let's look at an example for you chemists. Here we have a function called bracket c of t. Bracket c of t is a concentration. It's a concentration of some product of a chemical reaction. So I'm going to say that that concentration is measured in moles per liter. I apologize to you chemists if that's sort of an unusual unit. Maybe you speak about millimoles per milliliter or something like that, but I'm just going to say moles per liter. I also apologize if the common abbreviation for moles is not M. I kind of work far away from chemistry. I don't know their notation. But let's say that the units on this concentration are moles per liter. And let's say we're measuring time here in seconds this time. It's a chemical reaction. It's a function of time. So again, the units on the derivative, well, it's units of output per units of input. That's moles per liter per second. Or I guess if you want to pronounce that as moles per liter second, that's fine. And what is this integral telling us? Well, if you integrate, this time I'm just going to underline it while I say it, if you have moles per liter per second, and you multiply that by seconds, you get moles per liter. So the integral of this rate of change in this case is a change in the concentration. So it's the concentration at time 2 minus the concentration at time 1. And again, that's a positive number if the concentration is higher at time 2. The net change is positive. It's a negative number if the concentration is lower at time 2, right? So that's a negative net change. It would be equal to 0 if the concentration was the same at those two time values. Nice. So what are we doing? We're analyzing the dimensions on a rate of change and talking about the units rather, the units on a rate of change. And we're talking about the units on this integral. It's the change in the function. How about something from physics? Here, the quantity that we're measuring is the mass of a rod. Okay, so the mass of a rod, that's the output variable. Mass might be measured in something like grams, kilograms, some unit of mass. And that mass depends on how far we are from the left endpoint of the rod. So our input variable here is not time, but rather x, and maybe we're measuring that distance in centimeters. Okay, so this rod has varying density. The density at x centimeters from its left endpoint is called m of x. Okay, so the author is calling the linear density rho the derivative. What are the units on the derivative? Well, if the units on m are grams and the units on x are centimeters, the units on the derivative are grams per centimeter. So the units on this rho are grams per centimeter. Yeah, maybe I can write it in this time since they're small. Grams per centimeter, and we're multiplying that by what are the units on dx? The units on dx are the same as x. Change in x. So grams per centimeter times centimeters is centimeters. So this is the change in, grams, pardon me. Grams per centimeter times centimeters is grams. So this is the change in the mass of the rod from A to B. So it's the mass of the segment of that rod between x equals A and B. Yeah. So in physics, they kind of say if you integrate linear density with respect to distance, you get mass, because density is the change in mass with respect to distance in the one-dimensional setting. Cool. Let's look at one for the biologists. We talked about this in the past, that rates of change in biology are usually called growth rates. So the growth rate of a population, dn dt. So n is the output variable. It's a population. It would be measured in something like number of individuals. Typically for populations, those would be in units, like, millions of individuals. If it's a large population, thousands of individuals. But here I'm just going to write number of individuals. Maybe the units on t are time. So t is measured in time. So sorry, time is not a unit. Maybe I'm measuring it in years. Years is a unit. So the derivative, well, it's output per input. So it would be people per year, individuals per year. I switch them to people. So individuals per year. And what is the integral saying? It's saying that if you integrate the growth rate, you integrate individuals per year with respect to year, you get the net change in individuals. So this is the net change in the population. And again, the word net is being used because it might be positive, negative, or zero. Right? So this growth rate takes into account birth and death. So if this number is positive, that means the population over that time interval grew. It ended up bigger than it started. If this is negative, the population was in decline. It ended up smaller than it began. And if it's zero, it means that it kind of broke even. The population size at the end and beginning of that time interval was the same. Cool. So all kinds of interesting applications of the definite integral. Let's specialize to one more from physics, something that we've talked about quite a bit here, a particle moving along a line. If I denote by v of t the velocity, so I've implicitly called s of t the position, velocity is the derivative of position, then there are two integrals we might want to compute. The first one is just the direct application of the net change theorem. If you integrate the velocity with respect to time, well, because the antiderivative of v is s, you get s of b minus s of a. So that is, you get the position at the end minus the position at the beginning. And physicists call that quantity the displacement. So you're just keeping track of, again, moving along a line. Where are you at the end minus where are you at the beginning? That difference is called the displacement. So if we use, say, sort of left and right as the negative and positive directions, if this displacement is positive, it means that the particle ended up to the right of where it started. Yeah. If this displacement is negative, it means the particle ended up to the left of where it started. If this displacement is zero, it means the particle ended up exactly where it started. So the displacement just keeps track of the net change in distance, right? The net change in position, rather, I should say. If you want to know the distance traveled, you don't integrate the velocity function. You have to ignore the direction of motion. Well, the way to ignore the direction of motion and with the velocity is to take its absolute value, right? So if I put the absolute value signs around v of t, then I'm talking about the speed. The speed of the particle is the absolute value. It's the magnitude of the velocity ignoring the direction. So if you want the distance traveled, you have to integrate not the velocity, but rather the speed. So the speed is the absolute value of velocity. And if you think about what that's going to do, you're just keeping track of how fast you're going at each instant times the instance. So that's distance, right? Rate times time is distance. Okay, by putting the absolute value signs, we're ignoring the direction of motion, so we're going to pick up the entire distance that we travel. Okay, so let's end this video with a computational example. Well, before we do that, let's look at the sort of what we were just talking about as a picture. Here I've got a velocity curve drawn here in figure 3 taken from your book, and you can see that that velocity is positive sometimes. The particle is moving in the positive direction. The velocity is negative sometimes. It's moving in the negative direction. And then the velocity was positive again. So anywhere in this picture where the velocity is positive, that particle was moving to the right. And this area, A1, represents how far it moved to the right during that time interval. A3 also represents a distance of the particle moving to the right. But A2, it's a signed area. It's going to represent how far the particle moves to the left. The absolute value, the area actually of that yellow shaded region, is how far the particle moves to the left. So if you were thinking about the displacement of it, well, you would take how far you went to the right take away how far you went to the left and then add how far you go to the right. That's your displacement. If you want the distance traveled, you would just sum those three distances, right? Because you're not keeping track of which way you're going. You just want to know how far. Okay. So in practice, when you want to compute the absolute value, the integral of an absolute value, you have to determine where is the function positive and where is it negative, and split the integral over those intervals to find the relevant antiderivatives. So that's what I want to end with an example. And I've got this written out, so I'll just kind of narrate us through it. So suppose that we have a particle moving along a line, and we are given that its velocity function is that quadratic polynomial. We're measuring distance in centimeters and time in seconds. So v of t is t squared minus 2t minus 3 is the instantaneous velocity in centimeters per second. And I want to do two things. I want to find the displacement over the interval from 2 to 4, and I want to find the distance traveled over the interval from 2 to 4. Okay, so the displacement, we said, I'll just reveal the entire calculation here. The displacement is the integral of velocity. So I'm just taking my velocity function. I just hid it from you. You can stop the video and go back and look, but the velocity function was this quadratic polynomial. So if I want to find displacement, I integrate the velocity. And you can check the math here. I'm going to keep this video short and kind of go slow, but I've just written an antiderivative for that polynomial. And now I'm using the fundamental theorem of calculus. So in my first expression here, I'm just evaluating that thing at 4. Replacing t with 4 everywhere, and then I have to subtract. The second expression is evaluating it 2. Okay, I left out all the details. You can stop the video and check your own math here, but that ends up being 2/3. The units on that would be centimeters, and that's displacement. So what does it mean? It means that the particle ends up 2/3 of a centimeter to the right, because it's positive, of where it started. That's what displacement means. This particle stopped 2/3 of a centimeter from the point where it started. Okay. How do I calculate distance? Well, distance is the absolute value of velocity. Oops, sorry about that. So distance, I have to compute the absolute value, but I don't know how to find the antiderivative of an absolute value. So basically what I have to do is determine where is this quantity in the absolute values positive, where is it negative? Because where it's positive, I can just erase the absolute values, and where it's negative, I have to replace the thing inside of it with its opposite. Well, so we're experts at finding where functions are positive or negative. We make sign diagrams. So that's what I'm going to do, is I'm going to make a sign diagram real quick for v. So I took my velocity function and I factored it. It factors nicely. It's a classroom example. And I've got labeled here the two places where the velocity function is 0, at -1 and +3. And you can check my signs. I put them in already. The velocity goes from positive to negative to positive. So what is this business I'm putting in the sign diagram? It kind of looks like it doesn't belong here. It's the interval that we're considering from 2 to 4. Right? So this is just kind of showing me in particular that over the first second from 2 to 3, my velocity is negative. But over the second second from 3 to 4, it was positive. So when I go to evaluate this absolute value, over the first second from 2 to 3, I'll have to replace that velocity with its opposite. So let me show you that that's what I'm going to do down here. So the distance traveled, over the interval from 2 to 3, I'm replacing the absolute value with negative the velocity. That's because the velocity was less than 0 there, and the absolute value of something that's less than 0 is its opposite. From the 3 to 4, the velocity was positive, so I just erased the absolute values. Okay, so that's in general how you integrate an absolute value of something. You have to first determine where's the something positive and where is it negative. Okay, or negative and positive if I'm pointing at them. Everywhere it's negative, when you replace the absolute values, you replace the expression with its opposite. Everywhere it's positive, you just replace the expression with itself. All right, and now I multiplied that minus sign through there. I'll leave it to you to find the antiderivatives and do the arithmetic, but when you're all done, you should get 4 centimeters. So what is the conclusion? The object over the interval from 2 to 4 travels 4 centimeters, right? The total distance traveled was 4 centimeters. And we can look back at our sign diagram. Over the first second, over the first second, the object traveled left some distance. When you compute this integral, you'll know that distance. Okay, and then over the second second, the object moved back to the right. The total distance ended up being 4 centimeters. Its final position was 2/3 of a centimeter to the right of where it started. Okay, I hope that was helpful. Thanks for listening.